What would you prefer to discuss now?
Yeah, okay. So actually, I am reading your particularly interested in your recent paper, which is somehow a quantization of a lax
Yeah.
integrable system. But after I read it, I find out, yeah, still it's very different from conform blocks and and the so-called WZW connection. But
Um, do you think it's far? I think it's quite similar.
okay. Okay. So I noticed that you somehow you are actually considering a fixed Riemann surface and then considering a family of spectral curves over this fixed Riemann surface,
Yes.
right? And then um, you construct a so-called a sheaf of Lax operators, which is a certain meromorphic functions of with values in your vector space or something like that, or Lie algebra, and then you construct a connection over this so-called phase space. Now I'm wondering whether can we do something similar for a Hitchin system? Here, Hitchin system, I mean, we have a Riemann surface and we have a moduli space of so-called Higgs bundles,
Yeah.
and then it has a natural map to a certain affine space. So here, the affine space will parameterize a certain kind of spectral curves. I wonder, do we have some kind of, for example, conform blocks or connections in this setting?
Uh, uh, I guess I understood everything except for the last.
Okay.
The last was a question whether. Please
Okay.
repeat it.
Uh,
Say it
Let me
again.
state it in another way. So maybe this is uh, so we know that the fiber of the generic fiber of Hitchin systems are actually abelian varieties, and this
Yes.
abelian variety,
Yes.
in many cases, it also dominant the moduli space of vector bundles over the base Riemann surface.
Okay.
It dominate it. It can be proved that, and we know that in many sense the conform blocks are actually certain kind of sections of line bundles over this modular space of
Okay.
vector bundles.
Okay. Okay.
And then by this dominant map, actually we can somehow make these global sections um, uh, of line bundles on this moduli vector bundles to those uh, uh, lifted as sections of somehow as theta functions over these Jacobian spectral curves. Then we have also have a family of that kind of thing. Can we define some connections on on this vector space? Connections on this vector space.
Um, as understood, you are working. Okay, it is a quite different approach. I actually don't know any exact correspondence between these two approaches. You see, my
Okay.
approach is completely different. It's it's my approach with respect to quantization of Lax integrable systems, but it's our joint approach with Martin Schlechenmeyer to the West-Zumina-Witten-Neukov theory. Yeah.
Okay.
With respect to the whole model space of Riemann surfaces, it's our common work, joint work. And
Okay.
with respect to spectral curves of an integrable system, it's indeed my approach. Okay, but you see, the space of conformal blocks has quite different definition.
Right. It's very different.
Comparably to what you said. Yeah. I understand. I know this approach you said, but I never tried to establish any relation between these two approaches.
Okay.
Maybe in part it's done. In part it's done in the book by Andrei Turin.
Which book can
you? Which book? I actually don't remember its title. But maybe, but it's his only book on the questions of quantization and conformal field theory, Lagrangian, how to say, it's devoted to the relation between Lagrangian, what he called Lagrangian field theory, and algebraic field theory.
Okay.
Okay, if you wait, maybe if you wait a little bit, maybe
Okay.
I will be lucky to find out the title. To find out the title. Okay. So I found out the file, but I cannot open it because this is a new computer, and I have no program for reading PS files, PostScript files. Sorry. But if you just look for it in Google, I guess you will find it.
Yeah, okay. But
book by Turin. Turin, T-Y-U.
Yeah, I know. Okay.
So it's quite different approach. What I am doing and what we were doing together with Martin Schlichenmeyer is the following. You have certain moduli space of Riemann surfaces with no regard whether this is a whole moduli space or some its part. Yeah.
So also with marked points, right?
Yeah, for sure. Then we consider certain we consider, first of all, Krichy-Novikov algebras on these Riemann surfaces. These are, do you know, or I tell you?
Renal meromorphic functions with certain poles at points.
With fixed points where poles are allowed. Yeah.
Ah, okay.
Yeah. Okay. And these are exactly the marked points of the Riemann surface. Okay.
Okay.
So we consider a function algebra. Its tensor product by simply algebra, some analog of loop algebra.
Okay.
Okay. And besides, we consider what's called Krichy-Novikov vector fields, which are vector fields with the same conditions. They they only are allowed to have poles at fixed points. Well,
yeah.
Now, okay. We consider infinite dimensional over every Riemann surface. We consider an infinite dimensional module over all these algebras.
Okay.
Yeah. It is normally a model of semi-infinite forms.
Sorry, what do you mean by semi-infinite forms?
I'll just tell you. A model of semi-infinite forms over an appropriate space. Okay. What are semi-infinite forms? Let me tell you. I'll just show you the screen, okay? Well, if you have an infinite dimensional space with a base, say, with a base F1, Fn, and so on, you can consider you can consider external forms constructed of these symbols of the following form: F1, wedge, and so on, Fn, and so on. They are semi-infinite because they are infinite only in one direction. Now, it's not sensible to you can consider arbitrary external products of this form, you must require that they stabilize starting from certain number. I mean, starting from certain number m or n, capital N, they look like this. So they stabilize starting from number n. Okay, why it is important? Let me think a little bit, because I didn't think of this for quite a long time.
Okay.
So for example, it is important for the following reason. You need okay. Oh, sorry. Assume you would like not only have a linear space, but we want also have a model of a certain Lie algebra. Okay.
Yes.
Assume this was a model of a algebra A of Krichyver-Novikov functions. Krichyver-Novikov functions have certain bases, which are called surprise, surprise, Krichyver-Novikov bases. Say A1, A2, and so on, and also A0, A-1, and so on. Yes, and sorry, -1. Infinite, a base infinite in both directions. Okay, and they possess an important property that AI, AJ there is no it's not a grading, there is no natural grading, but there are certain almost gradings, which means the following, that it's a sum of Ci, J, K, AK, K from sorry, K from I plus J to I plus J plus, in this case, say plus some constant depending only on genus of the Riemann surface. Okay. What I have written here, this enumeration corresponds to a Riemann surface with 2 marked points. With 2 marked points. Okay. In this case, elements of Krichyver-Novikov base are enumerated by 1 index. Otherwise, everything looks a little bit more complicated, but to a certain extent, it's described in my text you have read already, okay? So to a certain extent. And it's also, we also consider such modules. Okay, this property is called almost grading, okay? Almost grading. You mean the range of this index k is finite. It is also natural to consider almost graded modules over A, okay? I mean AI, F, J, also some K for I plus J, to some constant C depending of genus, okay?
Okay.
C, I, G, not C, but now different coefficients.
Maybe L.
I don't know. G, I, J, K, F, K.
Okay.
Well, and range of this K is again finite. In this case, if you have such module, say F, then you can also define the A action. You can also turn these semi-infinite forms into a module. Okay? If you wouldn't consider this restriction,
Sorry, may I ask a question?
Yes.
So does your definition of the semi-infinite product depends on the order of the basis we choose?
Yes, it depends.
Okay.
Yes, it depends. You see, I know a work on independence, on independence on the choice of the base. I never had any time to understand it. Okay, but it's done by a person also from our institute, and when you appear in Moscow, you can talk to him.
Okay. Okay, thank you.
We can together talk to him.
Okay.
Well, for our purposes, it was always sufficient to have a definition using basis, you see. Well, so assume you don't consider this, you don't impose this restriction, okay? Then you will consider something, what shall you, what should you do? Okay. let me consider A here not as associative algebra, but as commutative Lie algebra. Then you can operate by Leibniz rule. Yes? Okay. A F1, say AK F1, F2, and so on, plus F1, AK F2, and so on, and so on. Okay? You cannot write the result in any finite form. Well,
I see.
Yeah. You will every factor will give you new expressions.
Yeah, yeah, I see. Yeah.
But
yeah,
with this condition, you have the following. Starting from certain number, you will have, let's say, semi-infinite monomials. Let me call it semi-infinite monomial, okay? You will obtain semi-infinite monomials with repeated factors.
So you mean the sum will stop at some after finite steps?
I mean, assume you operate by AK on this factor. Yes.
Yeah. Right.
AK F n plus 1 n plus 1. Yes. You will obtain linear combination of AK, AL with L bigger than this sum.
Yeah.
But all of them are contained here. Sorry, not AL, FL.
It's,
FL.
Right, it's FL.
FL. All of them are contained in this tail of the monomial. And for this reason, starting from this moment, you will obtain only zero monomials.
Okay, yeah? I see.
Okay.
Maybe a naive question about this. So what's the difference to consider the semi-infinite product of this F wet product if we just only considering the finite exterior product, but then we take, for example, direct sum or direct product to make it still a module over A. For example, in this case, you just
you see, normally, if I understood your question correct, I would answer the following: normally infinite dimensional algebras or Lie algebras do not have natural finite dimensional modules. They are completely degenerate.
Okay.
They're, I would say, hardly degenerate.
Okay.
This module is again infinite dimensional because the number n is not fixed. They can be of any length. This part can be of any length. Well,
yeah.
You see, for this reason, our approach. Okay, sorry. So our approach to conformal blocks is not really is not really our approach. It's approach by Tsuchiya, Ueno, Yamada. Maybe you know it's one of how to say basic works in this direction of conformal blocks. And
so do you mean by somehow the construct the conform blocks of the moduli of stable marked Riemann surfaces, and they construct a connection via so-called Sugawara operator? Do you mean that formalism? Okay.
Exactly. This is exactly what we Schechenmeyer and me also are doing, but with a different class of conformal and gauge symmetries. Tsuchiya, Ueno, Yamada do it with Kac-Moody and Virasoro algebras as gauge and conformal symmetries. We do it with Krejciever-Novikov algebras of affine type, of vector field type. Instead of Kac-Moody and Virasoro algebras. In some sense, our starting point was the following: that it's more natural because in the works Tsuchiya, Ueno, Yamada, and all preceding works, there appeared huge direct sums of Virasoro algebra. You see how you can give analytic object an analytic object like function or a vector field on a Riemann surface. You must fix some point and define and restrict them on small neighborhoods, and take Leroy expansions in these neighborhoods, right? This is what is actually done in the approach of Tsuchiya and Yamada, which actually go back to Boris Feigin. This is the name which you should know.
Fake. Oh, I know the name.
Okay.
Yeah, but I did not read his work.
What?
But I know this name. Yeah, it's very
Okay,
famous.
good.
But I do not know his work. Do not read his work.
So actually, the whole story goes back to him.
Oh, really? I did not know that. Yeah. Actually, what I read is somehow some modern treatment using people use it to prove the so-called Berliner formula, and yeah, it starts from the Tsuchiya to Japanese mathematician. Yeah.
And this is also these three Japaneses, yes?
Yeah. I'm familiar with these three mathematicians' work.
Okay. Well, so these two approaches deal actually with restriction of analytic object to neighborhoods of marked points. What we want to do together with Martin Schleichenmeyer is the following: to work with analytic objects, functions, vector fields as such. And this is why we take Cauchy-Verneuil algebras. Cauchy-Verneuil algebras are global algebras on Riemann surfaces.
So you mean that from their setting, they are considering somehow Cauchy algebra, which is a certain Laurent expansion over a marked point. So here you take the meromorphic vector fields. So you treat it as a more global one? I did not quite get that.
Why it is global object? Oh.
Right.
What is the question? Sorry.
Sorry, I did not quite get what you try to explain to me why we choose the Khrushchev-Novikov algebras. The choice is more natural, but I didn't get it. Why you say it is more natural? More natural
Okay.
choice.
More natural is a difficult category for whom how. But let me say, we certainly can. Okay, for example, okay, let me think a little bit. You see, I don't remember details. They can be found in my texts, in my different texts. But the point is the following. Anyway, everybody work with analytic object. It's only this only a question how we would like to give them. We can give them by a number of by a set of restrictions to neighborhoods of fixed points, or just work with them as such, with no. If you want, it's more invariant way.
Okay.
Okay. Maybe later I will explain it better. Okay.
Okay. May I also somehow ask a question? So, as you explained to me about the semi-infinite product, you also mentioned a grading or filtration on this Khrushchev-Novikov algebra. So, in your paper, you mentioned that filtration or that grading depends on a choice of a part of the marked point. I'm very confused by this. How does this choice of part of this marked point that gives this grading?
You see, assume you have, for the beginning, assume you have only 2 points. Yes? Then okay. A1 let's say P plus and P minus. Then say A1 is a function which has a simple zero at P plus and some order at P minus. If it would be just a Riemann sphere, the orders would be, say, the orders would be 1 and minus 1. But it's a Riemann surface of a positive genus, so we have a certain
a higher order.
Yeah, let's say if we consider here A with I, it has a pole of order I here and a pole of order, zero for the I here and a pole of order minus I plus J, something like that, plus G here. Yes? If you consider 2 points. And similarly with all other degrees. Let me say just now that there is a certain segment of indices which are not of positive and not of negative degree. Here we are basis elements of positive degrees, here of negative degrees, yes? And here something which has no definite degree. Okay. If you have many points, then to every splitting into 2 subsets, you can, with any splitting, you can assign similar picture. You say elements have zeros at this part and poles here, or vice versa, poles here, zeros here. Yeah? But if you take another splitting like this, you define different bases by different almost graded structure by saying that you have, say, zeros here and poles here and so on. You see?
I see.
So different splitting correspond to different almost graded structures. But what I wanted, but let me finish with conformal blocks. I would like to explain why it's completely different approach compared to what you said. And it's really a problem to relate them. It's really a problem to relate them. Do you understand what I mean?
So
it's really a problem to, there should be a correspondence between these 2 approaches. But nobody...
So you mean between the two approach to conform blocks?
Yes.
Okay.
As certain sections of
line models
bundles
or the rest of it?
bundles over Jacobians and
Okay.
okay.
Mm.
Let's say between theta functional approach and this approach, which I so you see, we proceed, roughly speaking, we proceed as follows. We proceed as follows. We construct, let's say, this module, which we denote by, say, f to semi-infinite degree, the semi-infinite power. And we have, we define an action of A of G tensor A. Oh, sorry. A, G tensor A. And of the Lie algebra of Cauchy-Verneuil vector fields here, by means of the procedure I described. Okay, now we choose a certain subalgebra, certain Lie subalgebra here, or better say here, which is called regular subalgebra. Regular subalgebra, R, say R. Okay. Roughly, it corresponds to negative degrees. Roughly, it corresponds to negative degrees in this Lie algebra. Okay. Well, but only roughly. And we take f, the module, the quotient of the module by the action of this Lie subalgebra. These are conformal blocks. I even don't have any proof that it's a finite dimensional space. So you see, the difference between these two approaches is huge, right? Nevertheless, they should be related. This is a problem. I don't know any answer. Why?
Okay.
But certainly, maybe in the book by Turing, he offers some, not really proofs, but some idea how it could be done.
Between these two approaches, you mean?
Yeah.
You mean some ideas to relate these two different approaches?
It's it's a difficult work. And
Yep.
so, which doesn't promise too much profit. I mean, mathematics, too much, you see, I'm not sure it will be really recognized now by mathematical community.
I see. I see. So, but I noticed that while your approach, it seems that you can construct the Hermitian metric a very natural Hermitian metric by using with the existence of evolution. However, it's an extremely difficult problem to construct a Hermitian metric on conform blocks. I mean, the method by Tsuchiya, Yuno, and Yamada. It's very difficult problems.
Yeah, I know.
To construct a Hermitian metric,
no,
right?
Also, it's a problem in other approaches because, for example, I discussed this with Jon Andersen. Maybe you know Jon Andersen in Denmark.
Oh, I know. I know. It's Denmark. He's in Denmark.
Denmark, yeah.
Uh-huh.
Jon Andersen in Denmark in
But I think he has a paper which claims the proof of unitarity of conform blocks, but the paper has never been published.
Really? Okay. He published so many papers that it's really impossible to read all of them.
Yeah, when Edward Langham, my supervisor, actually first suggested this problem to me, I found a paper by Anderson, which is maybe 7 years ago, which claims a proof of the unitarity of conform blocks in the setting of Tsuchiya, Yuno, and Yamada, but I never really understand his paper, and it seems that the paper has never been published. I don't know, maybe I remember not correctly.
But, it's necessary to ask him why he didn't publish it. Maybe
well, I did not
not everything is really done there.
Okay, I did not ask him, but it's.
You see, I published my text, but I actually said that it's the statement is modular a certain conjecture. Yeah?
I noticed. Yeah, I noticed that statement. Yeah. So yeah. So Professor, so I can find your work with. Sorry, I cannot remember the name of your collaborator, but I think you also mentioned the work in your paper, right? With
the name is the following.
Schleichenmeyer, right? So in your reference you have only one paper joined with him, which is in 2004. Do you mean that work?
I don't remember. We have two.
Sorry.
We have two. We have two joint works in Russian Mathematical Service. And I guess the last work is of 2013, something like that.
2013. Okay, yeah, I know.
And the first one maybe 2004. But it's not. But earlier we had a work on Sugawara construction for Chevernoikov algebras, and it was published in Journal of Soviet Mathematics. You see, in Western world, it's called Journal of Soviet Mathematics. Here in Russia, it's called different.
But I noticed that you marked it as a Russian mathematics survey, right?
Sorry?
It's published in a Russian mathematics survey, right?
So we have two works in Russian mathematical service.
Okay.
Like, let's say,
Sweet math.
something like this. But, these two are devoted to нижних замолочков connection. And this one is devoted to Sugawara construction.
Okay.
Let me also tell you that I didn't actually plan to, I shifted more in direction of integrable systems. See, and, oh, sorry. There is one more guy which wants to join, but he doesn't know that the lectures are. I'll just tell him, and probably.
Yeah, maybe I can leave. I think you have already explained a lot to me. If I have other questions, I can send you email.
We first ask him. Алексей, вы слышите меня?
Да, день добрый, Олег Карлович.
День добрый. Алексей, вы знаете, у нас сейчас вообще-то частная беседа, потому что лекции уже кончились.
Ясно.
Вот. Это перед вами один из слушателей, коллега из Китая, который в нашем институте будет работать в феврале, Ван Бин.
Ну, понятно. Ну, я хорошо. Извиняюсь, что ворвался к вам.
Ничего.
Тогда... У меня такой вопрос. Если будут вопросы по лекциям, я их вам в e-mail могу задавать?
Конечно.
Ну, отлично. Тогда я не буду вам мешать, как бы. До свидания, Олег Карлович.
Хорошо. Ладно, ну всего доброго. No problem. Алексей?
Yeah, okay.
He didn't leave.
So yeah, maybe I think I can leave now, and actually okay.
Alexei also left. So okay. I apologize for let's say two general answers, not really concrete. But as I said, I'm doing now integrable systems, and I also need to, how to say, I don't know how to say it in English. I only need to remind the things related to conformal blocks and so on, so on, so on.
Okay.
I also need to remind them because for quite a long time I didn't.
Yeah, actually, I recently I also somehow deal with somehow Higgs bundles,
Yeah.
but it's purely from the point of view of algebraic geometry, because I actually I tried to prove the unitarity, but it's very difficult. I do not have any idea to
But
prove it before.
I would ask to tell me about your attempts. Would be interesting.
You mean currently?
I mean, your results on unitarity and your results on Hitchin systems as well.
Oh, yeah, I only do some very small generalization. So before this somehow people can can prove that there is a dominant map from the Jacobian of spectral curves to the moduli of vector bundles.
Yeah.
And they can also talk about the generic fiber of Hitchin fibration. What I have done is try to add a certain kind of parabolic conditions to show what are the generic fibers are. Actually, if you add some parabolic condition and mark point, you mean you have certain filtration, and your Higgs field has to preserve the filtration or strictly preserve this filtration. Then you will find that all your spectral curves are singular. But it turns out that the spectral curves are singular, but their singularity are not that bad. We can take its normalization, and you will find the normalized spectral curve has some very good properties, and the ramification over the base Riemann surfaces actually corresponding to somehow a conjugate partition. You know, a filtration corresponds to a partition, but then you will find that after you resolve the singularity, you will get a conjugate partition, and which actually tells you how the parabolic structure comes from. If you push forward the line bundle on the normalized spectral curve and to the base Riemann surfaces, and you will get the desired parabolic structure. And we prove that you also have a dominant map from the from the Jacobian of the normalized spectral curves to the moduli space of parabolic vector bundles, which also means you have somehow the conform blocks next to theta functions. But after calculation, you will find these two space, the conform blocks, the space of conform blocks is of much less dimension, much fewer dimensions. So you cannot use it to get something meaningful.
You cannot use it for what?
You cannot use it. You cannot use the theta functions on this the Jacobian of the spectral curve to describe the conform blocks, because these two space are it's a very small subspace of theta functions. And on the other side, I also cannot compare. You know, there is a Hit equations over the space of theta functions, or a family of theta functions, and you also have the WDW connection of conform blocks. But it's also very difficult to compare these two connections, even you have this inclusion. So somehow my research stopped at this side.
I see. I see. Okay, I hope, you see, when I said I would be glad to discuss everything this with you personally, I meant really personally, not by Zoom, because anyway, it's quite.
I understand.
It would be better to discuss it really personally on the blackboard,
so,
okay?
Yeah. So, Professor, how's the conditions in Moscow now? How the pandemic affects your whether you will go to the institute regularly as before, or you prefer staying at home?
For the moment, most of our employees, most of members of our institute work at home.
Okay.
Work at home. And only certain people is allowed to attend the building. You see. You see, the situation is the following. They promised to start vaccination with the beginning of new year. And how many people will be vaccinated to February? I cannot predict.
Okay, yeah. Actually, my contract, or somehow my appointment, will start from the beginning of February. And yeah, but still I haven't to deal with somehow visa or working permit at the present. I don't know how things proceed at the present.
I see. So you see, my forecast is the following: that we will work more or less normally, starting from late spring or early summer.
I see.
This is my personal forecast.
Okay, I hope so.
Okay.
Yeah.
Okay. So if you get more questions, we can discuss it in Zoom.
Sure.
Okay.
Yeah, sure. Yeah, thank you.
Bye-bye.
Bye-bye. Thank you.